This Mathcast will walk you through section 12.3, where your students will learn techniques to bound the error of Taylor polynomials. Section 12.3 will complete our survey of Taylor polynomials and Taylor series that started back in Chapter 10, but was the major focus of Chapter 12. Now in this section, we will investigate ways to bound the inevitable error that results when a Taylor polynomial is used to approximate the value on a function that it models. And we will explore two different ways to bound that error. The first method, which will be the focus of lesson 12.3.1, can be applied to alternating Taylor polynomials only, while the second method, Lagrange error bound, will be the focus of lesson 12.3.2 and can be applied to all Taylor polynomials. For the first problem in lesson 12.3.1, problem 12-87, have teams work in pairs. And the way you can do this is, without opening their books, just read out loud part A to the class, which asks teams to sketch the graph of f of x equals cosine x and its fourth degree Taylor polynomial on the same set of axes. Now, each pair will make one large sketch that they can share and reference as we move forward. And what we'll do is, for parts B, C, and D, we can use a think, pair, share. This will keep the entire class working on the same part of the problem at the same time, and will give you an opportunity to summarize as necessary. So you might want to even not allow students to open their books at all for this entire problem, problem 1287, and read each part to them or project it as it comes. So the way this would work, the teacher will project and read part B only. Students will think quietly for a minute or two, and then the teacher will prompt students to write their individual answers on their paper. And after a few minutes, the teacher will prompt the pairs to share their answers with their partners, discussing where they agree or where they differ. And finally, after a few minutes, the teacher will prompt the partners to share their answers with their whole team, or if you prefer, to share out to the whole class. And then you'll repeat for part C and part D. Now, be aware that part D is a particularly interesting problem to summarize with the whole class. This question asks, what two factors influence the accuracy of a Taylor polynomial? Now, their answers to parts B and C should help them answer that question. From part B, they contrasted a fourth degree Taylor polynomial at two different values of x, and students should be able to conclude that the closer the value is to the center of the Taylor polynomial, the better the approximation would be. And likewise, from part C, they contrasted a fourth degree approximation with a sixth degree Taylor approximation at the same value of x, and from that, they should conclude that the higher the degree, the better the accuracy. Now, as they share out these conjectures and conclusions, write them on the board. And you might need to reference them when talking to teams in the future as we proceed through this section, because your students will be gradually making sense of how to define a margin of error, or how to bound an error for Taylor polynomials. Now, in the process of doing that, your students will learn some complicated looking formulas that they can use to bound error. Now, those formulas are useful, but what is most essential is that your students have a deep understanding of the conceptual foundation of these formulas. And these two summarizing statements that come from problem 12-87 part B will help to establish that. Problem 12-88 starts with our final mystery polynomial problem in this chapter. Now, this is a long question with 4 parts, A through D, which will guide your students towards solving the mystery polynomial challenge and simultaneously discovering how to bound the error of approximations given by Taylor polynomials that alternate, like this one, for ln of x centered at x equals 1. Now, before working through parts A through D, give teams about 5 minutes and no more to attempt to solve this mystery using guess and check. And in order to have any hope that they'll achieve this goal, which they're supposed to do without a calculator, you will need to provide teams with the clue that the decimal value for ln of 1.5 is about 0.405465. Now, their goal is to find a way to use a Taylor polynomial centered at 1 to approximate this value so that it's accurate within 2 decimal places. That is, they're going to need to find a Taylor that approximates ln of 1.5 as 0.40 or 0.41. So the question then becomes, what degree Taylor will guarantee this result? Now let your students play with this task, but still cut them off after 5 minutes or so to start parts A through D, where they will be guided towards a strategy that will find this answer efficiently. So part A will ask your students to make a prediction about the number of terms necessary for a Taylor that's centered at 1 to approximate the value of ln of 1.5 with the desired accuracy of 2 decimal places. Notice that this is a different question than asking what degree Taylor would guarantee such accuracy. So as you circulate, you might want to check and make sure that your students recognize this distinction. Next, in part B, teams will make a table of the approximations they find for ln of 1.5 using Taylor polynomials of degrees 1 through 8. This table could take a long time to complete, so as you circulate, encourage teams to find a way to divide up the work. And then part C will ask your students to make observations about the patterns they see on this table, and then to use that observation to predict what the Taylor, or P of 1.5, converges towards. Students should notice that P sub n of 1.5 is an oscillating function, they can see that on the table, and that it does seem to converge towards some number between 0.405 and 0.406. So most teams will predict 0.4055. Now, in part D, they will compare the predicted value with the decimal value that their calculator gave them, and then cross-reference it with the table to conclude that a 4th degree Taylor polynomial about x equals 1 yields the desired accuracy of 2 decimal places. Now problem 12-89 continues the investigation of the Taylor approximation about x equals 1 for ln of 1.5. In this case, your students will complete a different table where they record the value of the first 6 terms of this Taylor series and look for patterns among successive terms. Now, this is an important moment to stop and summarize after teams have had a chance to discuss observations that they see. Perhaps you could use a whip around, where each team prepares one or more statement to share with the class, and then the teacher pulls the class together and gives everyone opportunities to share what they notice. Now, if you choose, you could have each team write their summary statement on an index card and then collect the cards and project them as you read out loud. Or you could simply have teams verbally share their thoughts while you record the observations on the board. Either way, teams should notice that the value of consecutive terms alternate between positive and negative numbers, and at the same time, their absolute values decrease. This should bring to mind the alternating series test lesson from back in Chapter 10, Lesson 10.1.3. In that lesson, your students played a game where, on a number line, they moved a playing piece back and forth towards the sum of an alternating series. What they discovered was that when a series converges, adding or subtracting a term will cause it to jump over the sum to which the series will converge, either forward or backwards, depending on whether the term is positive or negative. Revisiting this game as a whole class will help your students visualize why the next term of an alternating series will be larger than the actual error of the approximating value. So knowing that when an alternating series converges, each term will decrease in magnitude in such a way that each partial sum, or Taylor polynomial approximation, will bounce above or below the actual converging value, the remaining parts of this problem, parts C through E, summarize how the value of the n plus 1 degree term will always overestimate the error of an n degree Taylor polynomial. Now, these are great problems to use as a carousel. Simply copy these 4 problems on 4 different chart papers or poster boards and have teams circulate from board to board, writing their thoughts about the answer to each problem. They do not need to do these problems in the order they are written. And when you are done, have teams do a gallery walk where they read what other students have written. Finally, problem 12-90 can be used to check for understanding at the end of class. In this problem, students will calculate the error bound when using a third-degree polynomial for sine of x, centered at x equals 0, to approximate sine of 2. Lesson 12.3.2 introduces the Lagrange error bound, which, like the alternating series error bound from lesson 12.3.1, will use the n plus 1th term to bound the error. The only difference here is that the value of the n plus 1th term will need to be over-approximated. Now, we're going to start in problem 12-99 by examining why the n plus 1th term is important. In this case, 3 different curves all have the same first-degree Taylor polynomial or tangent line centered at 1. Now, your students should notice right away that the concavity of these curves affects the size of the error of the approximations. Now, concavity, of course, is determined by the second derivative of the curve, which is a part of the n plus 1th term of a first-degree polynomial. So, after completing this problem, do a whip around with the whole class where your students will share their observations and conjectures about how the size of the next term of an nth degree polynomial might improve or worsen a Taylor polynomial approximation. Problem 12-100 uses the observations from the previous problem to demonstrate the Lagrange error bound and how it works. Your students might find this wordy demonstration to be a bit daunting, so use a study team strategy to help your teams work together to make sense of these steps. The listening post is a great study team strategy to use on a problem like this that involves a lot of steps and a lot of careful reading. The way listening post works is the work is broken up into 10-minute segments, and for the first 10 minutes, 2 of the teammates do the work, talking through the process out loud and preferably recording their work on a shared sheet of chart paper that the entire group can easily see, while the other 2 members have different tasks. One of them listens and asks clarifying questions, but does not share ideas or write anything down. And the last team member does not talk at all. Instead, that team member takes notes and writes about what they heard and what they observed. Now, after 10 minutes, the work stops and the note taker shares the notes and observations, and then the roles are switched for another 10 minutes. So problem 12-100 unravels like this. In part A, your students will write a general equation for a first-degree Taylor polynomial to f of x centered at 0, recognizing that if we were to use that polynomial to approximate f of a, then there will be an error, and that error will depend on the value of the next term at x equals a. Now, that next term has a numerator of f double prime of a, so part B tells students to let m represent a maximum value of the second derivative near x equals a. So, after writing this inequality, f double prime is less than or equal to m, they will be told to integrate both parts of the inequality, which is a step that you should be ready to discuss with teams. So, have a pocket question ready here. As you circulate, ask teams to explain why integrating both sides of this inequality makes sense, noting that m is a constant that is defined to be larger than every value on f double prime near x equals a. So after integrating, your students will solve for f prime of x, and then in part C, they're going to repeat this whole process to solve for f of x. Now, part D has them go through all of these steps again, this time attending to the lower bound L as well, noting in part E that the original expression for the first degree Taylor appears on both sides of this inequality. So in part F, they're going to write a new inequality that represents the error of this first degree Taylor, lying between the L and the M. This is the Lagrange error. And then in part G, they repeat all of these steps again to find the Lagrange error for a second degree Taylor polynomial. And finally, in part H, they write a general expression for Lagrange error for any degree polynomial approximation of a function. Problem 12-101 asks teams to find the Lagrange error of a third-degree Taylor polynomial approximation of e to the 0.6. In part B, your students will need to define an L and an M value. This can be tricky for students, so as you circulate, you might want to ask them to quickly free sketch a graph of the fourth derivative of e to the x, which of course is e to the x, and list any values that they know with certainty lie on that graph, specifically a value before and a value after 0.6. Now, recognizing that the graph of the fourth derivative increases on the interval 0 to 1, your students could safely define L as 1 and M either as E or as an over approximation of E, 3, depending on whether or not they want to use their calculator to evaluate the Lagrange error. In that same spirit, the next two problems challenge teams to define the M for a fourth-degree Maclaurin polynomial for cosine x, that's in problem 12-102, and a third-degree Maclaurin polynomial for sine of 3x in problem 12-103. Again, if your teams are stuck, ask them to sketch graphs of the next derivatives in order to consider the extrema of those functions. In 12-102, for example, since all derivatives of cosine oscillate between -1 and 1, your students will see on their graph that the maximum value of its fifth derivative is 1. But in problem 12-103, the fourth derivative of sine of 3x has a stretch factor of -3 cubed, so its maximum value would be 27. So this concludes our walkthrough on section 12.3, where your students explored ways to bound the error of approximations made with Taylor polynomials.